In today's lecture, we will be starting module 3, that is design of DC machines. First of all, let's discuss the different dimensions of rotating machines, that is main dimensions of rotating machines. In the figure, we can see a DC machine in which it is having a rotor, that is armature, this is the rotor, and the stator, which consists of north south poles. So this is the DC machine. Similarly, we have AC machines such as induction machines and synchronous machines. So whatever be the type of machine, in the case of a rotating machine, the main dimensions are diameter of armature core, length of armature core, and length of air gap between stator and rotor. These dimensions will be common for all the rotating machines. Now let's discuss some important parameters which are helpful for designing or which are very much important in designing DC machines. Those important terms are magnetic and electric loadings. Let's define some terms. Let capital L be the length of conductor, Iz be the current through the conductor, and B average be the uniform magnetic flux density in the armature periphery. Here we have to mention an important thing, that is let's consider the cylindrical armature of a DC machine. Here the length of armature core is capital L, as we have already defined. L is the length of armature core, and we will be placing armature conductors in the slots provided on the armature periphery. So the length of each conductor will be equal to length of armature. That's why here we have defined L as the length of conductor in meters. Now we are assuming that the armature is rotating, so we are considering a single conductor, and that conductor will be moving in the magnetic field. So if the conductor is moved through a distance x, small letter x, in the magnetic field, the work done is given by, the equation for work done is W is equal to force into displacement. Okay. So here the displacement is x, force into x. So the force on a current carrying conductor placed in a magnetic field is F is equal to BIL, where B is the magnetic flux density, I is the current through the conductor, and L is the length of conductor. So the work done, W is equal to, this is the force and this is the displacement. So force, here we have to substitute the terms. For flux density, this B average, and current through the conductor is Iz, and length of conductor is capital L, and x is the distance travelled. This is the work done. Next, the flux cut by the conductor when moved through a distance x is flux phi is equal to B average, that is flux density into area swept by the conductor. That is B average into area swept by the conductor is the length of conductor into distance travelled. So this is the flux cut by the conductor. Then the work is equal to phi into Iz. The work is equal to phi into Iz. From the previous section, we had the equation for work is equal to B average L into Iz into x. This was the equation that we have already written. Here B average Lx is equal to phi. B average Lx is equal to phi. So we have substituted for phi into Iz. So work W is equal to phi into Iz. In rotating machines, phi is the flux per pole, and P is the number of poles, and Z is the total number of armature conductors. In our previous equation, the work done when a single conductor is moved through a distance x was flux phi into current through a single conductor. Now let's consider the rotation of the entire machine. So it is having z number of conductors and it will be having p number of poles. So the work done corresponds to the flux p into phi, because phi is the flux per pole. So if there are p number of poles, the total flux will be p phi, and this is the current through a single conductor. If there are z number of conductors, then we have to write z into Iz. So the work done in one revolution of the machine is work is equal to p phi into Ziz. Here the term p phi is the total flux entering and leaving the armature. So it is known as the total magnetic loading of the machine. Similarly, Z into Iz is the sum of currents in all the conductors on the armature, and it is known as the total electric loading of the machine. So once again, let's define these terms. The total magnetic loading is defined as the total flux around the armature periphery at the air gap, and the total electric loading is defined as the total number of ampere conductors around the armature periphery. Next, we will discuss two more terms which are very much important, that is specific magnetic and specific electric loadings. First, specific magnetic loading. Specific magnetic loading is the average value of flux density at the armature surface. Flux density means flux by area at the armature surface. So by definition, B average is equal to flux per pole divided by area under the pole. That is, flux per pole is phi. Phi divided by area under the pole. So now let's see how the area under the pole is calculated. Let's consider cylindrical pole which is having a length capital L. L is the length of pole, length of armature, and let's consider the cross-sectional view of this machine which is having two poles, so north and south poles, and this is the armature. Cross-sectional view, this is the cross-sectional view and this is the side view. So here the distance between north and south poles, can be calculated like this. This is the distance between north and south poles, and the distance between adjacent poles is defined as pole pitch, that is tau. Tau is equal to distance between adjacent poles, and it is given by the armature periphery. Armature periphery is pi into diameter of armature, pi d. Armature periphery divided by number of poles. Here the number of poles is 2. If there are p number of poles, pi d by p will give you the pole pitch, that is distance between adjacent poles. And the area under the pole it will be equal to the distance between adjacent poles into the length of armature core. So pole pitch into length of armature capital L, that is phi divided by pi d by p into L, that is p phi. P will come to the numerator, so p phi by pi dl. P phi by pi dl is the expression for B average. So we can say B average is the total flux around air gap divided by area flux path at air gap. And the typical value of B average or specific magnetic loading for DC machines, only for DC machines, is 0.4 to 0.8 Weber per meter square. Usually in the question, when you are doing the problem, the value of B average will be given. But if it is not given, if you have to assume it, you should assume a value which comes in this range. Next is specific electric loading. By definition, it is the ampere turn per unit section. Unit section means unit length. Unit section of armature periphery. That is ampere turn per meter. Ampere turn per unit section of armature periphery. So AC. AC is the notation used for specific electric loading. Small letter a, small letter c. AC is equal to total armature ampere conductors. That is the product of current through the conductor and the number of conductors. That is the total armature ampere conductors divided by armature periphery. That is the circumference at the air gap. So, as we have already written, circumference of armature is pi d, and the total number of conductors is Z, and the current through the conductor is Iz. So, Iz into Z divided by pi d will give you the specific electric loading. And the typical value for AC in the case of DC machines is 15,000 to 50,000 ampere conductors per meter. And one more thing to remember is there is a relation between specific magnetic loading, that is B average, and the maximum flux density B max. These are two different terms, B average and B max. So the relation is B max is equal to B average by Kf, where Kf is the field form factor, or it is approximately equal to B average by psi, where psi is the ratio of pole arc to pole pitch. Pole arc is nothing but the dimension marked in this figure. If this is the pole shoe of one of the poles of a machine, say north or south pole, and then B is the pole arc. The length of pole arc is defined by the notation small letter b. So it is equal to pole arc by pole pitch is equal to b by pole pitch is denoted by tau. B by tau will give you psi. So B max is equal to B average by psi. This relation will be helpful for solving some problems. Thank you.